Okay, so we are continuing in Chapter 8, Section 1. I apologize, in the last couple of videos we've been in 8-1 the whole time. Okay, so we're continuing with hypothesis testing, and we are going in sequence. There's a lot of elements to talk about when we're talking about hypothesis testing and developing the introductory theory behind it. So yeah, we've got a lot of stuff to talk about. The next thing is the critical region, so-called critical region. So let's just, before we get into that, let's just go back and kind of describe what happens. So we go out, we gather data. We might be interested in the population in all community college students in California, and we might be thinking about the statistic or the parameter for this population. Yeah, I shouldn't say statistic, that's for a sample. Parameter is the population. We might be talking about the mean age or something like that. Okay, and so what we'll do is we'll go out and gather a sample, and we'll look at its value. We have no way of knowing what the true population parameter is because we simply cannot access the whole population. Let's just say. So we will go and sample different students within this population. We'll look at different ways to differentiate between different samples, and so we'll look at this data and we'll notice that some values are very similar to one another, and so we might draw a conjecture and say the average looks like it where these average values all are, and we might get different data from a different sample that appears to be distinctly different, and so we might say, well, what is it about that sample or that subsection of the population? Why is its data distinct? And we might try to develop a statistical hypothesis about that, a conjecture as to why that's happening. And then from there, our next logical step would be to go and test that hypothesis. And so what we're talking about when we're talking about the critical region on our x-axis here, let's suppose we have no way of knowing that this is here. So this is, let's go and make this the secret. All right, so nobody knows this. That's the true population parameter, okay? And we will go out and collect a bunch of data. We'll say, okay, look, we got this sample and its average is here. We got this sample and its average is here, and here we got all of these little data points for our samples, and they appear to be all pretty similar to this. Those are all pretty standard, and from different subsection of the population, their average values may be all over here. And so, we might have one that's in this sort of standard range. But if we're noticing that our values are over here, that might cause us to say, okay, well, look, it appears that for this population, whatever it is, the average is larger than whatever that value happens to be. Okay. So that draws us to what we're going to talk about right here. What is the critical region? The critical region, definition. Okay, so the critical region is the range of test values that indicate. So the test value, by the way, is the calculated value from our sample. So we take a sample and then we calculate the correct statistical test value, and that numerical value will tell us, well, let's see, is it in this range of values? Then that indicates that there is a significant difference between the value stated in H subscript 0 and the true value of the population parameter, and that H subscript 0 should be rejected. Okay. So, in other words, what this means is, we're seeing that there's anomalous data that's coming in this range over here, and here is the standard sort of range, and so our prediction might be that mu is actually greater than whatever this is, 5. I don't know. Okay. And so we're going to go out and take our own data, and it's going to land somewhere in this range. It's going to be either close to here or way over here, or maybe in here. And we're going to say, okay, well, I know it's not going to be exactly equal to 5. If it is, that would just be a coincidence. Remember, I don't know what this value actually is. I'm just picking out a number that I'm assuming that it's close to, and I'm giving it a look-see. If I get values over here, then I don't have data that's indicating that the true population average is greater than 5. If I'm seeing values that are in here, they might be a little less than 5, they might be a little greater than 5, but all of those values, we would just say, oh yeah, close enough, 5, right? There's no difference between our population parameter and 5, right? And if we're getting a sample that comes out with its statistic, way over here in this range, we would say, yeah, that is significantly greater. So we would throw away the initial hypothesis that says mu is equal to 5. That's H subscript 0, and we would, we would say reject that and go with the alternative hypothesis. But the problem is how much greater than it does it need to be? That seems like it might be within the standard range. Is that far enough away? What about that? All of these values in the middle. Where is the exact cutoff value for the values that indicate that there is a significant difference and we should reject H subscript 0? So another thing to notice here is the verbiage is sometimes we call this the rejection region. So if we end up in the rejection zone, we have to reject the null hypothesis, H subscript 0. Okay, so let's go ahead and determine how do we find these critical regions. That's what we'll talk about after I figure out how to flip the page. Now, there are various different types of hypothesis tests, and basically these are referring to the critical regions, or one way of remembering what type of test you're using is to get a mental picture of what the critical region looks like. So in a one-tailed test, we have two different options. We could say this is a left-tailed test, like this, and that would be the critical region in a left-tailed test. That would be shaded in like such, right? In a right-tailed test, we would have this area shaded in here, okay? Now, let's just quickly review. In all cases, you know, H0, the null hypothesis, not like that. The null hypothesis says that there's no difference. So let's say mu is equal to some number, call it k. All right. For a left-tailed test, our alternative hypothesis is going to take on this form. It's going to look like mu is less than k. Right? And here, our alternative hypothesis, as you might have guessed, is going to be mu is greater than k. All right. So let's move on down. Okay. A two-tailed test, that is our other option, and so we'll draw a little sketch of the distribution and show you what's happening there. So there's our normal curve. Technically, remember, it doesn't touch the axis here, so just redraw that just a tiny bit. Doesn't have to be perfect. Okay, that's what I keep telling myself. All right, so here we have, I'll just say k, and that's the middle of this distribution, okay? And on this side over here, and this side over here, we have our rejection region. So, No, if it's supercritical, we'll go back up here and change these to K. And then just ended up making a big mess of it. All right, so in a two-tailed test, we would be saying, of course, H subscript 0 is stating mu is equal to K, right? And our alternative hypothesis, H subscript 1, here, in this case, would state simply mu is not equal to K. All right, now, how do we define the cutoff for our critical region? What are these values on the left and right hand side for, the case of a two-tailed test? Or, what is this value right here? Or, for example, what is this value right here? Well, the way that we will determine that, in each of these we have a significance level for our test. In a left-tailed test, we're going to find the test statistic. So it will depend on what distribution we're using. If we're using the t distribution, this will be a t value, right? If we are using the normal distribution, that will be a z value. Well, what are we doing? We're trying to find that specific value. This is known as a critical value because it defines where the critical region begins, such that the area underneath the tail of this is alpha. So over here we're going to be finding another critical z value such that the area in the right tail over here is alpha. And for a two-tailed test, as you might imagine, the total area that is divided up amongst these two tails is alpha. And so that means, essentially, since our normal curve is symmetric, that each half has an area of alpha divided by 2. So this instance that we're in right here for a two-tailed test might look very, very familiar. And we'll pause there.